Very good morning, my dear students. Now we are going to discuss the topic Ionic equilibrium lesson. Common ion effect, buffer solution, working of buffer solution, buffer capacity and buffer index. The last one, Henderson equation. So in this session, we are going to discuss these are the topics one by one we will see. Question number 1. What is common ion effect? Given example. Let us consider you have to take two salt. The salt one is dissolved in water. If the salt is dissolved in water, we have known that the charge separation occurs. That's why the salt is disappeared. By the taste of the salt, we can identify the solution, we can identify the salt is dissolved, right? Now, you have to regain the salt in the solution. So what we have to do that? Another one salt, little bit we have to add it. So which type of salt we have to add again? We are going to add the salt should have the common ion of the dissolved salt. Now, let us see the statement. The reduction of the degree of dissociation of a salt by the addition of common ion is called common ion effect. The reduction means what? Suppressed or reducing. The degree of dissociation means what? Charge separation. The degree of dissociation is reduced by the addition of common ion. I hope you can understand. With the example, the first salt, silver chloride, is dissolved. The charge separation, what are they? Ag plus and Cl minus. Right? Now, you have to get again the dissolved salt in the same solution. So little bit you have to add sodium chloride salt. It is added. So when we add the sodium chloride, what will happen? Silver chloride also has the Cl minus ion. Sodium chloride also has Cl minus ion. The Cl minus ion is a common ion. By the effect of the common ion, the charge separation present in right hand side, it is reunit. The reaction shift to the left hand side. So we can get again silver chloride. So another one example, ammonium hydroxide dissolve in water ammonium ion and hydroxide ion. When we add the ammonium chloride, ammonium act as a common ion. So right side charge separation again join, because ammonium concentration increases, the reaction shift into the left hand side. We can get ammonium hydroxide. The same common ion effect we can see in the third example also. Acetic acid charge separation H plus and CH3COO minus. When we add the sodium acetate salt, CH3COO minus act as a common ion. So right side CH3COO minus concentration increases, then acetate ion CH3COO minus combine with H plus and the reaction shift into the left hand side. We can get acetic acid again. So it is important 3 more question, the statement and with the example we have to write it. Let us move to the next question. What is buffer solution? Mention its types, give example. We have heard about titration method. Mostly in the titration, acid versus base. Suppose in the burette, you have to take sodium hydroxide. In the pipette, you have to take hydrochloric acid. Anyway, the base versus acid or acid versus base, anything we can take it. So when we titrate against any two of the solution, one of the solution in which we are going to find the titer value, that kind of solution is contaminated. Any one of the solution maybe is contaminated. So little bit we have to add the buffer solution. Why? Because while we are titrating, the pH level it maintains constant. For the reason we are adding the buffer solution. Mostly in industry level, we can utilize the buffer solution. Now we see the statement. A buffer solution is one which maintains its pH fairly constant even upon the addition of small amounts of acid or base. Right? A buffer solution is one which maintains its pH fairly constant even upon the addition of small amounts of acid or base. Here, what are the types of buffer solution? The first type, acidic buffer solution. Acidic buffer solution. So a weak acid together with a salt of same acid with a strong base. Actually, the solution containing acetic acid and sodium acetate. Acetic acid and sodium acetate. A solution containing a weak acid, acetic acid, and its salt. That is called acidic buffer solution. Okay, another one type, what is that? Basic buffer solution. A weak base and its salt with a strong acid. With a strong acid. That is called basic buffer solution. Here, ammonium hydroxide and ammonium chloride. The solution containing ammonium hydroxide and ammonium chloride. So, two types of buffer solution. One is a acidic buffer solution. Another one is basic buffer solution. Anyway, we have to take weak salt and its weak acid. Another one is weak base and its weak salt. Right. How is buffer solution working while addition of acid or base? How is buffer solution working while addition of acid or base? So when we add the buffer solution in any acid or base, how it is working? Here, acidic buffer solution, it is given acetic acid and sodium acetate undergoes charge separation in the solution form. The equation is given. So we have known if an acid is added to this mixture, it will be consumed by the conjugate base CH3COO minus to form the undissociated weak acid. The increase in the concentration of H plus does not reduce the pH significantly. If a base is added, it will be neutralized by hydronium ion, and then acetic acid is dissociated to maintain equilibrium. Hence, pH is not significantly altered. Actually, what is a statement? Is going to say that common ion effect. Common ion effect. Suppose a buffer solution, acidic buffer solution is added in acid. Acid, we know that dominating H plus means acid. The H plus concentration anyway increases. The increased H plus concentration again join with the acetate ion CH3CO minus. So the equilibrium shift into the reaction shift into the left hand side. So acetic acid will form. Suppose base is added. In base we know that OH minus combined with the H plus, it gives a water. So anyway, the solution will be neutralized. Like that, the pH is maintained. OH minus H plus gives water. Now, question number 4. What is the effect of 0.8 molar of acidic buffer solution after adding 0.01 molar NaOH, sodium hydroxide? Here, the buffer solution concentration is given 0.8 molar. It is added to the 0.01 molar sodium hydroxide base. So what is the level of the pH? Whether it is altered or not, we can check it by the derivation. First you should write buffer solution concentration, level and degree of dissociation. Here 0.8 minus alpha, alpha means degree of dissociation. So initially is nothing, that's why minus alpha is given. For acetate ion alpha and H plus ion, that also alpha, right? First you should write the buffer solution concentration level in the beginning. It is mentioned in equation 1. Equation 2. Equation 2. For the first equation, we should write the Ka. Equilibrium constant K, A for acid. So product concentration CH3CO minus H plus divided by reactant concentration CH3COOH should be given within the bracket means concentration. That is second equation. Next, third. So you have to bring H plus concentration alone left hand side. So H plus concentration equal to Ka. Ka is multiple with the denominator in this previous equation. So here it will come in the numerator. So acetic acid will come up with the concentration divided by acetate ion CH3COO minus. This is equation 3. This equation, third equation, just you set in your mind, because by using this equation we can solve. This is another one, 5 mark, that is Henderson equation. H plus concentration equal to Ka, acetic acid concentration divided by acetate ion concentration. Now, in the acetic acid concentration, initially, what you have written 0.8 minus alpha minus 0.01. After 0.01 molar NaOH is added, what is the condition of buffer solution? That's why we can apply the value divided by 0.8 plus alpha plus 0.01 concentration. It's for acetate ion. So numerator acetic acid, denominator acetate ion. It is in equation 4. Equation 5 you see. The alpha is removed. Why? Because when we compare the degree of dissociation with 0.8 molar of buffer solution, the degree of dissociation is negligible small. the value is very, very small. That's why it is negligible. So remaining alone we can write it 0.8 minus 0.01 concentration divided by 0.8 plus 0.01 concentration. Now, after subtraction and addition, we can get it H plus concentration equal to Ka 0.79 divided by 0.81. H plus concentration equal to Ka into 0.79 divided by 0.81. 0.79, how it comes? 0.80 minus 0.01, we can get 0.79. Then 0.81, 0.80 plus 0.01. So numerator for acetic acid, denominator for acetate ion. Now Ka. Ka equilibrium constant for acetic acid is 1.8 into 10 to the power minus 5. 1.8 into 10 to the power minus 5. It is given, right? Just you have to substitute the value in the previous equation. So we can get H plus concentration equal to 1.8 into 10 to the power minus 5 multiple with 0.79 divided by 0.81. Now the H plus concentration value 1.76 into 10 to the power minus 5. That is equation 9. So we know that the pH formula, what is that? Negative logarithm base 10 H plus concentration. So pH equal to minus log 10 H plus concentration. This formula we have to use it for getting pH value. So pH equal to minus log the place of H plus concentration, just you substitute the value. So 1.76 into 10 to the power minus 5. The next step, the 10 power minus 5 will go front. So minus minus cancel. So plus 5 minus log 1.76 will come. Log 1.76 value in logarithm table we can find it 0.25. So 5 minus 0.25. So we can get the pH value 4.75. 4.75. The addition of a strong base 0.01 molar NaOH increased the pH only slightly. That's why it's from 4.74 to 4.75. So the buffer solution is, buffer action is verified. So question number 5. Write a notes on buffer capacity and buffer index. Write a notes on buffer capacity and buffer index. It is defined as the number of gram equivalents of acid or base added to 1 liter of the buffer solution to change its pH by unity. So what's the formula? So beta equal to dB by dpH. Here dB means what? Number of gram equivalents of acid or base added to 1 liter of buffer solution. pH means what? Change in the pH after addition of acid or base. That is called buffer capacity and buffer index. Now we are going to see the last question. Very important, 5 more question. Derive Henderson Hasselbalch equation. Usually we are saying Henderson equation. The first step, H plus concentration equal to Ka, equilibrium constant with acid. So Ka equal to acid concentration divided by base concentration. This equation is got from the dissociation of acetic acid. So numerator CH3COH, the denominator CH3COO minus. So combine with the sodium means the salt will form, right? That's why the acetate ion here act as a base, conjugate base. Next step, the base turns to salt. So H plus concentration equal to Ka, acid concentration divided by salt concentration. Salt concentration. The concentration of conjugate base CH3CO minus is nearly equal to the initial concentration of the added salt. That's why the base CH3COO minus conjugate base turns to salt. Third, so both sides you have to take log. So log H plus concentration equal to log Ka plus log acid divided by salt concentration. Next, so both side multiple with the negative minus, then only we can get a pH. So minus log H plus equal to minus log Ka minus log acid divided by salt. So we know that pH equal to minus log H plus and pKa equal to minus log Ka. That's the formula. This formula we should apply in the previous step. So here pH, H is here, so minus log H plus, likewise pKa, Ka is here in left side, so minus log Ka. Okay, after applying the formula, so we get pH equal to pKa minus log acid concentration divided by salt concentration. So in the place of minus H plus concentration, pH will come minus log Ka, pKa will come, so minus log acid concentration divided by salt concentration. Suppose the denominator will come into the numerator, means sign will change. So pH equal to pKa plus log salt concentration divided by acid concentration. Thank you.